We will now do a discussion of an introduction to probability in section 5.1. Chapter 5 has 3 sections, and the first section deals with mainly 2 concepts, mainly the law of large numbers and conducting simulations, which may seem a bit confusing at first, but once you get used to doing them, it shouldn't be too much of a problem. But first of all, what is probability? And probability is basically the likelihood that an event will occur. And for instance, like let's say if you have a group of people, and let's say if you have 4 Germans in this group, you have 3 French, and let's say you have 5 Spaniards. And so you're asked this question: what is the probability, if you randomly select one of these people, and there's 12 of them, what is the probability you'll select a German? And so this is our notation for probability, the probability that event G will occur in essence. And so the probability of German is just going to be the total number of ways of having a success, so to speak, 4 over the total possibilities, which is 12. And actually, you can leave your answer just like that. You don't, in AP Stats, you don't have to simplify it unless you're asked to do so, or to create a decimal. And that is considered showing your work right there. Frequently, if you just put a naked answer, meaning if you just put like 0.3 repeating, that's certainly correct in the mathematical sense, but to show your work, show your fraction like that. And so this is what we call the theoretical probability, in the sense that it's based on the concept of equally likely outcomes, and it can be calculated exactly. So there's really 2 ways that, in essence, we're going to look at probability. And one is kind of what I just explained, is that probability is equal to the total number of possible successes, of possible what we call success. Now, success doesn't necessarily mean a good thing in context. The success could be defined in the problem as having a disease or getting in a car wreck, or what's the probability of catching a cold, that sort of thing. So success doesn't necessarily mean a good things in context. Total number of possible outcomes over the total number of possibilities. So, and this is, in essence, a theoretical probability. So if you roll a fair 6-sided die, what's the probability that you're going to roll a 1? Well, there's only one way of having a success, and 6 total possibilities to be 1 out of 6. What's the probability with a standard deck of 52 cards that you're going to get dealt a king? Well, there's 4 kings, and there's 52 possibilities, so it'd be 4 out of 52, or 1/13. And so those theoretical probabilities can be calculated exactly, but there's some probabilities that we will not be able to calculate exactly, and that is, in essence, empirical probabilities. And empirical probabilities, you really just have to look at long-term relative frequency. Long-term relative frequency. And that is something like, what's the probability when I'm driving home that I'm going to get stopped at the traffic light in the parkway? Well, there's no way to calculate that exactly. The only way to estimate it is to look at a large number of trials every day when I drive home, just to record whether or not I have to stop at that traffic light. When I go in the grocery store, what's the probability there's going to be 3 people in line in front of me? Well, no way to calculate that exactly. The only way to estimate it is look at a large number of times when I go in the store and note the percent of the time that that there's 3 people in line in front of me. Or for instance, if you're rolling this die, this pig dice from the game Past the Pigs, what's the probability of rolling a trotter? In other words, what's the probability when I roll it that it's going to end up on its feet like that, standing up? Well, there's no way to calculate that exactly. The only thing you can do is look at long-term relative frequency. In other words, to roll this die a large number of times and note the percent of the time that it ends up on its feet like that. And so empirical probability we're going to be working a lot with. A probability is always a number that is between 0 and 1 inclusive, between 0 and 1. It can be expressed as a fraction, as a decimal, or as a percent. Any of those ways are fine. So then we have what is known as the law of large numbers. That is the first main concept really in the chapter, and that is this. And basically it's this: the larger your sample size is, the closer your estimate, in other words, your statistic, your estimate, and in general, we have p hats or x bars for a proportion or for a mean, will be to the true population value. And we'll be looking at several examples of this in class. And so, for instance, like let's say if we were estimating, we want to know the percent of times when you flip a fair coin that you get heads. Well, that's the true population value is 50%. And so let's say if I flip the coin 10 times and I get, let's say, 4 out of 10. So my estimate for that is 0.4. In other words, it's a pretty good percentage off. And in general, what the law of large numbers says is that if you have a small sample size, your estimate tends to be far off. But the bigger your sample size is, the closer this estimate is going to be to the actual value. So assuming we don't have any sort of bias in our system. So if you wanted to know, let's say RP is the percent of the time when you roll a die that you roll a 1. So our population value is 1/6. Now our sample value, I just roll it a number of times, it's going to be different from that. But the bigger my sample size is, the closer my estimate will be to the actual value. And so, and this concept is sort of the basis for a number of things we're going to do in formulas we're going to have in statistical inference later in the year. But in class, we're doing an activity with M&Ms. And so what is, what is the proportion of M&Ms that are brown? And so the actual, and so we made a little graph when we did that. And so on our x-axis, what we had is this was our sample size. All right, we started out with 0 and then 1, so forth, and it went on, let's say 10, 20, and 30. We were just looking at sample size, the number of M&Ms that we had. And then what we were measuring is the percent of brown ones, the percent of M&Ms that are brown. And so we scale this, let's say 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So 10 to 100. You only have to put 2 numbers down per scale to get credit for scaling. And so the actual true value, I think, is like 16%. So it was somewhere around like that. That is the actual percent of values. That is the percent, so RP, 0.16 repeating. That is the percent of M&Ms in the world that are brown, I think. And in our estimate, what happened is that, well, when we had 0 M&Ms, it wasn't brown. On the first M&M was brown, so then it became, 100%. And then the second and third one were not brown, like that. And so what happened was, and so we measured the percent, and so after 5 M&Ms, we had 1 of them brown, so that's at 20%. So it went something like this and like that, and then after 10, I think we still had just 1 of them that was brown, like that. And so the bigger the sample size was, the closer our proportion got to the actual value, the closer RP hat here. And so, that picture is a very famous picture of the law of large numbers. Whenever you have a really small sample size, in general, your estimate is going to be not close to the actual thing you're estimating. But the bigger your sample size is, assuming you don't have any sort of bias, okay? Assuming you don't have any bias, your sample proportion will get closer and closer to the actual value. And so this is somewhat of a famous type graph of the law of large numbers, and that's the first big topic in the chapter. And then the next big thing is the concept of simulating. And a simulation is just basically setting up a system to mimic, using a chance behavior, a proportion. And you may say, well, why should we do this, especially after we're going to learn the things in Section 5.2 and 5.3 and in Chapter 6 when we can calculate these things exactly. But simulations are popular things to do when you have to calculate really, really complicated probabilities, and you set up a simulation and you have a computer do it like 1 billion times over, and you can see what what value the computer is converging to figure out these probabilities. But so anyway, so in this situation, it is believed that 20% of tomatoes in a large container of tomatoes are rotten. Perform a simulation of a random sample of 10 tomatoes. All right, and so what you do here is, in essence, you're going to set up a system with that proportion. All right, so our P, our proportion, is 0.2. And so I'm going to use random digits. I'm going to use a random digit table, which I believe I have handy here. And I'm just going to get random digits off of one line of this table. And I'm going to say this. I'm going to say let 0 and 1 represent. So let 0 and 1 represent a rotten tomato. And then I'm going to say let the other numbers, so that would be 2 through 9, represent not rotten. So not rotten. Okay, like that. And so thereby, 20% of the time, in general, I'm expecting to get a rotten tomato. Okay, and so what I'll do is I'll just go to the first line here and start getting random numbers. So this first line in this random number table, and so that's 1, 9, 2, 2, 3. So the first numbers that I have is 1, 9, 2, 2, 3. And then and it asks for a sample of 10 tomatoes. Each one of these numbers represents a tomato. And then the next numbers are 9, 5, 0, 3, 4. And so I've got 10 numbers there. Now 0 and 1 represents rotten, so that represents rotten. And so 9 is not rotten. That would be not rotten, not rotten, non-rotten. 9 is not rotten. 5 would be not rotten. 0 is rotten. And then 3 is not rotten, and 4 is not rotten. So when you look at it, in my simulation, 2 out of 10 were rotten in my simulation. And that is how you do a simulation.
Excuse the interruption. We're going to have our last attempt to get the remaining students that need to complete the demographics for the PSAT. These students are in your room. You need to send them to the focus room in the media center. Riley O'Brien, Kaylee Battle, Chandler Buss, Cameron Christian, Lavelle Copeland, Elizabeth Cortez.
All right, so now what we've got is this is one of the more complicated ones that we could have to do a simulation. So we still have the situation that P is equal to 0.2, is that 20% of the tomatoes are rotten. So in the context number 2, Sven randomly selects 5 tomatoes and notices that 2 of them are rotten. So he got 40% of his, not 20%. He wonders if this is evidence that more than 20% of all the tomatoes are rotten. Sven wants to perform a simulation to estimate the probability of getting 2 or more rotten tomatoes in a sample of 5, assuming that the 20% figure is correct. So, and so we're going to perform 10 trials of this and see how often it happens that we would have 2 or more rotten tomatoes just by chance, assuming this 20% figure is correct. Or is it just so unusual to happen that we would reason there's something wrong there, where, hey, I'm getting 40% in my sample, and the claim is that only 20% are rotten. And so now in the next chapter, we're actually going to calculate this exactly, in other words, in a theoretical manner. But we're going to sort of do it in an empirical way here. And so what I'll do is I'll set up the same thing. And so we have, let 0 and 1 represent that it's a rotten tomato. And then let 2 through 9 represent that it is not rotten. Okay, and so what I'll do is I'm going to get a sample of size 5, and so I'll just go to let's say line 104 here, and I'll start getting lines of random numbers. So this would be 5. So this would be 5, 2, 7, 1, 1. Well, in this particular sample, I've got 2 out of the 5 that are rotten. Well, that actually matches Sven's thing, and so I continue on 3, 8, 8, 8, 9. So in this one, all of those are not rotten, so that'd be 0 or 5. And it says it wants me to do 10 trials. So each of those is a trial of size 5. So I've got to do this 10 times. So here we go. So this would be 9, 3, 0, 7, 4. So in this one, we just have 1 out of 5 that's rotten. And so then we've got 6, 0, 2, 2, 7. That one has 1 out of 5 that is rotten. And then we have 4, 0, 0, 1, 1. This one, we have 4 out of 5 that is rotten. So that's certainly a lot. And then we have 8, 5, 8, 4, 8. And so this one we have 0 out of 5 that's rotten. So I need 4 more of these things. And then we've got 4, 8, 7, 6, 7. That's 0 out of 5 that is rotten. And then we have 5, 2, 5, 7, 3. And so that's 0 out of 5 that are rotten. And so a couple of more. And so then we've got 9, 5, 5, 9, 2. That is 0 out of 5 that are rotten. And then lastly, 9, 4, 0, 0, 7. So that would be 2 out of 5 that are rotten. And then, and so what percent of the time, so what percent of the time did we get 2 or more that are rotten? Well, that happened in this one. So this one. And this one, that happened in 3 out of the 10 times. So that is our estimate of the probability of getting 2 or more rotten tomatoes out of 5, assuming that the whole population is 20% rotten. In other words, getting more than 20%, more than 40% in our sample. And this is an example of a small, 5 is a really small sample size, so there's going to be a lot of variability. And the actual true probability here is somewhere, I think it's like 26% or something like that, is the true probability, and that is our p-hat, that is our estimate of it. And so that's an example of a simulation. And then lastly, you can do a number of different things to perform a simulation, not just a random number table, but using random integer on your calculator, or you can even use a die or a deck of cards or a number of different things. So in this case, it says 25% of households in a city do not have clean tap water. Explain how you would organize a simulation. All right, so our P is 0.25. And so how could we use a fair six-sided die? Well, there's a number of different ways you could do it, but one way is to just say, well, if I roll a 1, roll a 1, let that represent no clean water. No clean water in a house. And then let 2, 3, and 4 represent that it has clean water. And then if I roll a 5 or a 6, I ignore it. I just act like it didn't happen. I just roll the die another time. So that sets up a simulation that would mimic 25%. And so then, what about a standard deck of 52 cards? And we're going to get into a more thorough explanation of that. Of what, hey, I don't know if not everybody's familiar with a 52 card deck, but 1/4 of the cards are diamonds and hearts, and those are the red cards, and then the black cards are spades and clubs. And anyway, so what could we do to represent 25%? So you could just pick one of the suits. So let clubs represent no clean water, and then let diamonds, spades, and hearts represent clean water. And so that would, and then deal a card. So you have to say what you're dealing. So you would say deal 1 card. That represents in essence 1 trial of this thing. So in this one, what you're in essence doing is roll the die. So you have to kind of say exactly what you're doing in the simulation. So with a random number table to represent 25%, now when you're doing with this random number table, you got to set it up like this. So you would say select 2 digits. Select 2 digits. Okay? And so you would say let 0, 1 through 25. You can't just say 1 to 25. Say let 0, 1 to 25 represent no clean water. And then let 26 through 99, and also 00, 26 through 99, represent clean water. And so then you would, in essence, go to the random number table. So in this first line, you would say, well, 19, take the first two digits, that represents no clean water. And then 22, that represents no clean water. And then 39, you kind of jump over the gap there. That would represent they do have clean water, and so forth. And you keep going on. But like 09, like right here, remember to include, so if it's the ones with single digits has to be a 0 in front of it. So make sure and write it like that. And then using a graphing calculator, what you can do is use random integer, and you can just say, let 1 to 25 represent no clean water, and then 26 through 100 represent clean water. And then generate a random integer between 1 and 100. And so the function in your calculator is what we're going to call, it's the random integer function, and I'll show you that in a second. And so we would go from 1 to 100. So that's my lower value, and that's my upper value. And then we'll just pick one number, all right, or in essence, however many you want. And so on your calculator, to get to that function, if you turn the calculator on, and if you go to the math button right there and you hit math, then you arrow over to probability and then go down to random integer right there. So random integer, and go lower value 1, upper value 100, and just pick one value, and then hit enter. And so 76. And so 76 would be the first one, and that would represent no clean water. And then to perform that same operation again, just hit enter again, and it would generate the next one as 35, and that would also be no clean water. So that's, kind of a quick run through of a simulation and the law of large numbers.